Okay, so I'd like to just do a brief revisit of moments. It would help if you had your CGP Mechanics and Stats book, and I'm looking to start with at page 112 and example 2. We've got a light rod, which remember means the rod has no mass of its own, and it's being supported by two forces acting upwards, and there are two masses, one at each end of the rod, and we're asked to work out the values of those two masses. So here is a diagram of that situation, and slightly unusual because normally we would perhaps have supports here which would have reaction forces. We're not actually told what these forces are, but there we go, they're in that position. I've marked the distances, and there are a couple of ways of approaching this, but hopefully you can remember that the way to start is to either take moments about A or B. So if I'm taking moments about A, this force has no effect at all, but the other forces have a twisting effect, and some of those forces are twisting the rod clockwise and some are forcing it anti-clockwise, and because we're told that this rod is in equilibrium, the clockwise moment and the anti-clockwise moment must be equal. And to work out a moment, you take the force and you multiply it by the distance from the pivot point, and that officially is the perpendicular distance, although in this case it's nice and easy because everything is perpendicular. So looking at moments about A, I've got three things acting. I've got this force which is shoving it anti-clockwise, I've got this force which is shoving it anti-clockwise, and I've got this force which is pulling it clockwise. So the clockwise moment is that force multiplied by 10, its distance from A, and the two anti-clockwise forces acting in opposition are this one multiplied by its distance 2, and the 90 Newton weight is a total distance of 7 meters away from the pivot point. And so doing a little bit of calculation, I can work out the value of the mass. Remember, that's the mass, not the force. So this mass here is 9.39 kilograms, but its weight is 9.39 g. And make sure you store that on your calculator because we're going to use it again in a minute. Now, to work out this force, I could do exactly the same with moments about B, and I would get exactly the right answer. Taking moments about B, this force would have no effect, so you'd have these two acting clockwise and this one acting anti-clockwise. But there is a quicker way of doing it, because you can also resolve the forces. So if I resolve those two forces, I can say, okay, resolve vertically, I've got two forces pushing up and two forces pushing down, and again the equilibrium means that they are the same. So there's no consideration there of distance. This isn't a moment, we're just saying that if this thing isn't moving, the total forces up must equal the forces down. And I know what MB is, I've just worked it out, it's 9.39, although that's I've got an exact value stored. And so blah 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 blah, I get a value for MB. Sorry, move that up a bit. MA, sorry, get a value for MA. So that's the sort of problem that we were solving with moments. Okay, so the second question I'd like to look at is on page 111, question 7. Again, we've got a light rod, no mass involved, no weight, and it's pivoting around this point O. And we're not told the total length, we're just told that this length is variable, this length D is variable, and we want to know what range of values of D would cause this to rotate anti-clockwise. Okay, so I've done a sketch of the problem here, and rather than worrying about it moving anti-clockwise, this is what they want us to work out, what length of D will make it move anti-clockwise. I'm going to assume equilibrium. I'm going to assume that it's not rotating and work out the value of D that would give me that. Now, clockwise equals anti-clockwise as before. If that's my pivot point, then this force here is going to be pulling it clockwise, as is that force there. They're going to be moving it in a clockwise direction. This force is going to be moving it anti-clockwise, as is the 25 Newton force. They're going to be moving it this way. And you may remember that this force here at an angle presents us with something of a problem. What we were doing before is we were saying, okay, because moment is force times perpendicular distance, we were extending that force line and working out the perpendicular distance. And this was really fiddly. So I am grateful to Axel, who proposed a different way of doing it. What we can do instead, and this is really easy for us now we have been resolving forces horizontally and vertically, is instead of doing force times perpendicular distance, we can do perpendicular force times distance. So for this force at an angle, what I need to do is work out its component in this direction. Now I know this angle here, 150 take away 90, is 60. So the component of this force in a vertical direction is going to be 24 cos 60. So the moment of that force will be 24 cos 60 multiplied by 5. So let's work out our moments. So our clockwise moments, if you remember, we've got this 4 Newton force, and that is at a distance of d plus 1 meters. So that's the moment for that force. We've also got this force turning it clockwise, so that is 38 times 2. And then force is turning it anti-clockwise. I've got 25 newtons times 1. And I've got this force at an angle, and I'm going to be using 24 cos 60 multiplied by 5. Let's sort it all out. Expand the bracket. 4d plus 4 plus 38 times 2, that's 76, equals 25. Cos 60 is a half, so that's 12 times 5, so that's 60. So I've got 85 here. I need to take away 80, so that means 4d equals 5. So d is equal to 1.25 meters. Now that means that when it's in equilibrium, d is 1.25 meters. Now, you need to ask yourself this. If d was longer, this 4 Newton force, which is turning it clockwise, would have a greater moment, because moment is force times distance. So if d was longer than 1.25, it would turn the bar clockwise. But we want to know what that length of d would turn it anti-clockwise. So basically, anything less than 1.25. So d is less than 1.25 meters would see anti-clockwise movement. So 1.25, it's in equilibrium. Longer than 1.25, it would rotate clockwise. Shorter than 1.25, it would rotate anti-clockwise, and that's what they wanted us to work out. So I'd like you to have a go at page 116, question 9, where you've got a rod. This time the rod has a mass, a centre of mass, which isn't in the centre. It's 2.7 metres from the end. It's 6 metres in total. And it's being supported by 2 strings at angles. So I'd like to have a go at this yourself, but just to start you off, here's my diagram of the problem. I'm going to start by taking moments about A, and then these forces don't count. You'll need to take moments about B as well. And remember my new suggestion, or Axel's new suggestion, rather than doing force times perpendicular distance, do perpendicular force times distance. So when I'm taking moments about A, this force, that's its perpendicular component, so that will be 20 cos 10 degrees. And then in the second part, when you have to take moments about B, well, if I know that angle there, I could say it was T cos that angle there, and of course that angle is 90 minus alpha, but as we know, it's easier for this one to say this is T sine alpha. So that's the perpendicular component there. So the perpendicular component here is 20 cos 10, or 20 sine 80. And because I don't know this angle and therefore can't work out that angle, I'm using T sine alpha. Anyway, have a go at that question and then pause the video and come back and you can see my solution. Okay, you ready to see my answer? So I think I left you with working out that clockwise equals anti-clockwise, taking moments about A, and you've only got one force pulling it clockwise, it's this one, so it's mg times 2.7, and then the one pulling it anti-clockwise is this one, so I use the perpendicular component, which is 20 cos 10 or 20 sine 80, times by the distance. Now I originally did this as 3.3, but of course the distance from the moment point A is actually 6, so there we go. So I fiddle about with that to get the value of m, and I stored that on my calculator because I'm going to need it. Now this next step was the fiddly bit. In the first example I did, I said how you could take moments about B, but it's easier to just resolve vertically, because the two forces going up, let's come down a bit, so T sine alpha and 20 cos 10, those two forces are going to be the same as mg. Forces up equal forces down. No moments there at all, that's just resolving. Trouble is here I've got two missing values, so I can't work it out from that. And I'd scratch my head a bit for this one, but you resolve horizontally as well. So forces going this way must equal forces going that way because it's in equilibrium. And there is a horizontal component of this force, which is T cos alpha. And there is a horizontal component of this force, which is 20 cos 80. They are the components pushing in on each other, and they must be the same. And it's quite easy to rearrange that as a T equals equation. And what I can then do is take that T equals equation and substitute it in here. And you might see what's coming now. So I rewrite that equation, replacing T with 20 cos 80 over cos alpha. And here I've got a sine divided by cos, so it becomes a tan, and then it's just sort of algebra, shift tanning it to get the answer. Pause that if you want to see that. And don't forget I want to find T as well. I've got a nice easy equation here for the value of T. So I store that value and substitute that in and get my final answer.